having me, and thanks to everyone for attending. I'm going to talk about some work I did together with Jonas Hirvonen fairly recently, but which builds on other work done before, and I'm also going to give a fairly broad overview of what I think is important in this area, I guess. So the framework or the background to this discussion, the context, is cosmological first order phase transitions. Here's a picture of the dynamics of such a phase transition. This is something a picture which comes from a numerical simulation done by Dan Cutting, David Weir, and Mark Hindmarsh. So as you go from left to right, we have three slices through snapshots of such a cosmological phase transition. Early on, bubbles nucleate, bubbles of the new phase. So as the universe grows and cools, at some point it cools below some critical temperature, at which point bubbles can nucleate of the new phase. Those bubbles grow because it's energetically favorable for them to do so. They collide, their collisions create fluid flows, and those fluid flows in turn create gravitational waves. And those gravitational waves free stream and redshift, and in principle are visible today with a sensitive enough detector. And not only that, so gravitational waves offer us some kind of observable remnant of any phase transition in the early universe, in particular a first order phase transition. But other things such as the matter-antimatter asymmetry could have been produced in a phase transition in this electroweak baryogenesis setup, for example. Also topological defects and the cosmological magnetic fields that we observe today all could have been produced in a phase transition. And so those remnants give us a new probe of particle physics, which in principle can compete with colliders, or can tell us different and complementary information. Focusing on the gravitational waves, they were discovered or seen directly now quite a few years ago in 2015, and published in 2016. Here's the first observation by one of the detectors of LIGO. This was done together with Virgo on the right. And so far, we've basically seen the loudest or the brightest gravitational wave events nearby, so black holes colliding relatively nearby. But in principle, with more sensitive detectors, we can detect more sources, and there's a kind of rich experimental program of designing and developing new gravitational wave detectors with increased sensitivity or sensitivity to different frequency ranges. And here I've given a picture of the kind of early stages of LISA, the laser interferometer space antenna, which should be launched in the 2030s and should in principle be able to see a phase transition or the gravitational waves of one at around the electroweak scale. And this is the kind of pipeline. This is how one could, in principle, constrain particle physics using gravitational wave detectors. And it kind of invoking this, like, well, if there were a phase transition in the early universe, this is from a LISA paper here, this 2019 paper, and this shows the pipeline from top left to bottom right of starting at some particle physics Lagrangian, your QFT, your underlying model, which is a standard model plus whatever. From that, you calculate these phase transition parameters. So you want to know what the order of the transition is, its temperature, and some other quantities. Those then go into these numerical simulations we saw, which involve fluids and the production of gravitational waves. From that, you get the spectrum. From the spectrum, you can then compare that to LISA sensitivity, and in the end, you can get a signal-to-noise ratio as a function of frequency, which, so that's the kind of the way that experiment and theory overlap here. And in principle, there's an inverse pipeline starting from an observation and trying to work out what you could constrain about particle physics or early universe cosmology. I'm going to focus on this first step, the kind of QFT step of calculating these phase transition parameters from an underlying model. So focusing in on those parameters, I'm going to split them up into three kinds, to equilibrium, purely equilibrium parameters, which only depend on homogeneous fields, kind of the simplest parameters, and then the non-equilibrium ones, near and further from equilibrium. And yeah, so one can imagine, so I've got a couple of pictures here, one can imagine some order parameter, something which tells you what phase you're in. So for the kind of liquid gas transition would be the density of the density, but it could be some scalar field in early universe, or some effective scalar field, or some observable which tells you which phase you're in, and there's an effective free energy for that observable, or an effective potential. And here I've shown one which has two minima corresponding to two phases, one at 0 and one at non-zero value. And the phase transition is first order if those two phases coexist in a range of temperatures with a barrier in between. In that case, you have a first order transition. And yeah, so these once you know the order of the transition, assuming it's first order, there are four parameters that really determine the gravitational wave spectrum. And so there's a couple more which are basically equilibrium parameters. That's the critical temperature and the latent heat. But then the critical temperature defined as the temperature at which the two phases have the same free energy. And then the most non-equilibrium physics, or the more non-equilibrium physics is associated with the bubble, and the most non-equilibrium physics of the bubble is looking at its late time evolution, and it's the speed at which it grows if you kind of let it just interact with the plasma. That's a really non-equilibrium calculation, but in between these two, there's a kind of near equilibrium calculation of how quickly you produce bubbles, the bubble nucleation rate. And from the bubble nucleation rate, you can get a bunch of other parameters which really directly go into the gravitational wave spectrum. And so it's a really important parameter for determining the gravitational waves. And yeah, that's what I'm going to focus on. And so in determining these parameters, so together with some collaborators, so here there's a plot from work with Thomas Tenkinen, but this kind of follows work done by together with Gina Kroon and Graham White and Philip Schichol and Thomas as well, where we looked at the theoretical uncertainties in this first step, calculating these phase transition parameters and how much that affects the gravitational wave spectrum. And this is basically a summary, in some sense, of a lot of that work. So on the y-axis, you can see there's the gravitational wave amplitude normalized in a cosmologically relevant way. And on the x-axis, you can see there's the frequency in a log-log plot. And the black line gives you a kind of laser sensitivity. That line roughly corresponds to a signal-to-noise ratio of 1. And then these two bands, green and blue, are theoretical predictions. They're theoretical predictions from one physical parameter point. In here, I've written the XSM, which is the standard model plus a real scalar. So just one new degree of freedom. And yeah, in one physical parameter point, we've done these calculations, and then we've looked at the renormalization scale dependence of the resulting gravitational wave spectrum through these phase transition parameters. And in a perfect calculation, there would be no renormalization scale dependence. So this scale dependence gives you a measure of the theoretical uncertainty of your calculation. And here I've shown two different approximations, a kind of more standard approximation, which is called here order G3 in green, which involves a resummed one loop calculation. The effective potential is basically calculated to order G cubed T to the 4. And then an improved calculation, which involves some two-loop diagrams and it calculates the effective potential up to order G to the 4, T to the 4. But and so what you can see from this plot is these uncertainties are pretty huge. So these error bands on this log-log plot, you can see there's the amplitude varies from 10 to the minus 15 to 10 to the minus 20 roughly. In the green case, there's 5 orders of magnitude uncertainty. And in the improved case, there's still roughly 2 orders of magnitude uncertainty in this prediction, which is not great for a theoretical prediction. so there's an important point and a caveat that here about these approximations. These kind of improved approximations were only applied to the equilibrium physics. So this is reducing these uncertainties as going from this green to blue band corresponds to improving your equilibrium calculations, but not improving your bubble nucleation calculations. And we were essentially able to see in this paper that the residual uncertainty in this blue band is mostly due to the calculation of the bubble nucleation rate. And as a consequence, it's kind of the limiting or a limiting source of uncertainty in predicting this gravitational wave amplitude, and hence in the idea of constraining particle physics from gravitational wave experiments. Okay, so that was my kind of intro motivation for phase transitions and gravitational waves and why we should care about the nucleation rate. I'm going to go on to talk about what I think is the status of thermonucleation theory and some important things. And then I'm going to talk about classical nucleation theory, and then I'm finally going to talk about the EFT approach. Okay. Moving on to the status of thermonucleation theory. Here's a potted history. So in chronological order, I've picked out some important papers, essentially, in the history of this topic. So at the top here, I have Lange's 1969 work, which essentially defined and solved for the nucleation rate within a classical statistical setup. So within classical statistical field theory or statistical mechanics, the nucleation rate was calculated there. And I'm going to talk about that a bit later. But kind of moving on to starting with the quantum field theory, the first really kind of important work in this field was by Coleman and then Callan Coleman, a pair of papers. These are a fate of the false vacuum. Famous papers where they looked at vacuum decay at 0 temperature, and they built a formalism to calculate the rate of decay of that involving something called a bounce. This was then built upon and generalized to the non-zero temperature independently by Affleck and Linder in 81. Those generalizations actually conflict, but anyway, they're sort of similar-ish. And then there was further work building on that. Here are a couple that I want to point out. In the early 90s, people studied radiatively induced transitions. And then people applied functional renormalization group methods and calculated one-loop corrections. So starting back at Callan and Coleman, 1977, the idea was, so starting with some theory with a tree-level vacuum potential at 0 temperatures, which looks a bit like this one here. So there's two minima, one which we call the true minimum, which is the kind of global minimum on the right, and then one which is a false minimum, which is metastable on the left. And then the idea of Callan and Coleman was that if you set up a vacuum state purely around this false vacuum, it should be unstable to tunneling, and hence the energy of that state should have an imaginary part. And then if you look at this first equation here, if you look at the probability of staying in that vacuum, this is the false vacuum to false vacuum transition rate, and amplitude squared, the real part of the energy cancels in the amplitude squared, and all that's left is the imaginary part of the energy, and you get some kind of decay rate, which looks like this. So then this false vacuum, after a long time, decays away. And they argued in these papers that this imaginary part of this energy can be calculated in Euclidean time. So you can rotate t to it. And then looking at this amplitude, this false vacuum to false vacuum amplitude, but now in Euclidean time, the kind of steps were to introduce the unit operator, to introduce a sum over all possible intermediate states, and then noticing, a unit operator of energy eigenstates, essentially. And then looking at large times, large tau, so in large Euclidean times, basically the kind of vacuum case, only the smallest energy survives, or rather the smallest energy survives the longest amount of time. So you can calculate this E naught in a Euclidean setup using a Euclidean path integral in vacuum. and then combining, and then they basically combined these equations to come up with this equation in the middle here, which gives you the rate of decay in terms of the imaginary part of the logarithm of this Euclidean vacuum path integral. And then that was calculated semi-classically by expanding around the saddle points of the action. This path integral has boundary conditions such that it's in the false vacuum at infinity, because you're imagining it starting in the false vacuum. And so you're looking for saddle points of the action, which go to the false vacuum at infinity, and which solve the Euclidean saddle point equation. And the Euclidean saddle point equation is very much like the Minkowskian one, except rather than t minus v, you have t plus v. So as a consequence, you have an upside down potential. So that's why this upside down potential. And they found two solutions. There's the false vacuum, that's the solution, stays in the false vacuum for the entire time, satisfies the boundary conditions. There's one other solution, the bounce, which starts in the false vacuum, moves over towards the true vacuum, goes over the kind of barrier between them, and then comes back again, bounces back again. And these two solutions then go into your semi-classical expansion of your path integral, and in the end, you can get the following result for the rate. So on the right-hand side, you can see, this is the rate. On the right-hand side, you can see kind of the most important part, this e to the minus Euclidean action evaluated on the bounce. That's the most important part because it's exponentially large. And then there's these prefactorial parts, which correspond to fluctuations around the bounce, in the usual kind of semi-classical or saddle point approximation of an exponential integral. So those fluctuations are split up into fluctuations which don't change the action. So the zero modes, crucially moving the bounce doesn't change the action because the whole thing is invariant under translations. So those factor out as the zero modes, and then there are the non-zero modes, most of which are positive because in moving or changing the bounce in most ways increases the action. But there's one negative mode which decreases the action, and that negative mode was argued to kind of to relate to, or to basically give this imaginary part, which hence relates to the metastability of this false vacuum. So this is a standard well-known result. Has been rederived and kind of reappreciated and re-looked at recently. Here, I pick out a couple of papers. There was this one in 2016 where they used the phrase direct approach, and they did in fact do a kind of more direct approach than Callan and Coleman's. They asked what's the probability of staying in the false vacuum in a kind of quite a direct probabilistic way, in assuming that it's basically decay is slow. So this kind of TNL basically gives how the timescale on which you decay and come back again, and so assuming that that's slow. And yet assuming that fluctuations within the vacuum, within the metastable vacuum, the false vacuum, are relatively fast compared to the timescales you're interested in. So in that kind of double scaling limit, they reproduced Callan and Coleman's result. So this kind of funny Euclidean negative eigenmode thing. So kind of putting on stronger foundations, in some sense, this old result. It was also looked at, again more recently in a completely real-time approach, starting from the optical theorem, using using Picard-Lefschetz theorem, so kind of complexifying the time. And anyway, they also reproduced Callan Coleman's result. So it's on, in some sense, rather solid footing. So that was the vacuum case. So generalizing that to non-zero, and in particular to high temperatures, which is what I'm going to be interested in today. This was done independently by Linde and Affleck in the same year. And Linde's approach was to take the vacuum energy result, which is minus 2 times the imaginary part of the energy, and to kind of bump it up to the thermal kind of analogy, which is the free energy instead of the vacuum energy. So this can be seen as like summing over the vacuum decay rate, summing with a Boltzmann weight. That's the kind of the idea behind it. And Linde found this result, or put forward this result. So it's rather similar to the Callan Coleman one, but it's not exactly the same. So there's now a 3D rather than 4D action, and the action contains within it not the tree level potential, but some kind of thermal effective potential. It was actually made kind of relatively ambiguous in this Linde paper, what exactly this VT should be. Yeah, there's only 3 zero modes instead of 4, and there's a factor of T out front. Yeah, otherwise relatively similar. So Affleck's paper started with quantum mechanics and looked at the decay rate in quantum mechanics, in assuming that there was some tree level potential which had these 2 minima. And then Affleck's result at high temperatures, although Affleck reproduced Linde's result ish in terms of the prefactor at low temperatures, at high temperatures found a different result. So there's no T here, there's a 2 pi, there's a plus here. So it turns out that at high temperatures, the negative mode doesn't contribute at all. You can write it out front, but it cancels. So there's basically no negative mode contribution. And the potentials are different. So there are these high temperature generalizations. They're not completely derived from first principles, but they're not a million miles off either, and they disagree with each other. So, I mean, how do we proceed? First thought, should we use the tree level potential? As Affleck suggested, it's the easiest thing we could do. There are some kind of obvious ways in which this doesn't work, because the tree level potentials is independent of temperature. And as the bounce equations solve the equations would then solve the equations with the tree level potential, that means the bounce would be independent of temperature. Which means if there's going to be a bounce at some high critical temperature, there also has to be a bounce at 0 temperature. But yet at 0 temperature, the phase structure might be completely different. Typically, there's no phase coexistence at 0 temperature, even though there is at high temperature, which means there's no bounce solution at 0 temperature. So this kind of fails on kind of straight away in that case. But even if there were phase coexistence at 0 temperature, if thermal effects kind of lift the 2 phases relative to each other, and if they do so in a way which is leading order compared to the tree level potential, then the tree level potential is not a good approximation. So it's kind of 2 ways in which we can see the tree level potentials maybe not the right place to start. Following on a bit more from Linde, maybe we could use some effective potential. What is the effective potential? It answers the question, what's the contribution to the energy from non-zero momentum fluctuations in the tree level potential around a homogeneous background, which I've called phi bar telling you that it's homogeneous, just reinforcing that point. So at one loop, the effective potential, or the correction to it, looks like this. There's a sum integral, sorry, the sum is there because we're at this thermal, and basically it's sum over fluctuations with a logarithm. The energies of the fluctuation. So this is like the mass, but it's the second derivative of the tree level potential around this background homogeneous phi, and then we have the momentum contribution, the p-squared contribution. So that kind of makes sense as a quantity if you think about looking at how the energy changes around the minimum of a tree level potential. Here I've shown for this is actually I've shown a kind of real world example of a tree level. This is the standard model tree level potential, where I've added the Higgs to the 6 operator, just to kind of get a kind of simple toy model for looking at phase transitions in near standard model theories. And what I've shown is the tree level potential together. I've put a factor of half so you can get it on the same axes with the high temperature potential at roughly the critical temperature. In blue and red. And what you can immediately see is there's an imaginary part of this high temperature potential, as well as a real part. And why would this be? Well, the effective potential tells you about the energy from fluctuations about a homogeneous phi bar. And that's a reasonable thing to do if you're fluctuating around the minimum. But if you want to fluctuate around a point like here, say 200 GeV, then you're fluctuating around a point which is obviously unstable. It may have v dash dash negative as well as a linear term. And if you look at fluctuations around that, there will, because v dash dash is negative, there'll be some contribution where p squared plus v dash dash is also negative, where p squared is sufficiently small. So these are kind of long wavelength things, small p squared. And yeah, those give an imaginary part because we have a logarithm of a negative number. And you can think of those, and this was pointed out or discussed by Weinberg and Wu, this imaginary part corresponds to decay of these states. So if you start with a homogeneous state here, and you ask what the contributions to the energy are, you get these imaginary parts, and they correspond to decays, just as they did before. But this is now a completely different, physically different decay. This is no longer bubble nucleation. These are decays which happen with really rather large p. So if you take p to be basically arbitrarily small and positive, you find that this is this decay. So these are large but inhomogeneous configurations, which tell you that this is unstable. And my argument here is basically that this effective potential is maybe not physically the right thing, as well as having an imaginary part. It's kind of, yeah, it's maybe not asking the right question. So the standard definition of the effective potential is using a Legendre transform, but there's an alternative definition due to Fukuda and Kyriakopoulos, which is the one I'll use here, and which agrees, which is, it's just the integral over these non-zero momenta. So if you have the full partition function top left, you can split that into the integration of the constant mode and the integration of the non-constant modes. And doing the non-constant modes first gives you the effective potential. So this effective potential has an imaginary part, so we definitely can't use it for the bounce equations. This imaginary part has nothing to do with bubble nucleation anyway. Can we use just the real part? Maybe, I mean, because that would be kind of ideal if we could just use the real part. So what happens if we do it? We're imagining here that we want to calculate the nucleation rate, and we're going to start with some kind of partition function which looks like this, where we put the real part of the effective potential in. Maybe that works. But if we use these equations to write out what the real part of the effective potential is, so just rehashing those equations up there, you can see that in calculating the real part of the effective potential, I've integrated over all the non-zero momentum modes. And I'm also having to integrate over them here in this measure. So to be able to put it into the path integral, I have to integrate over all non-zero momentum modes twice. So as a consequence, we're double counting basically all the modes apart from the zero momentum mode. And in addition, we're making an uncontrolled derivative expansion, because here when we calculated the effective potential, we did so on a constant background, whereas when we're calculating the bubble nucleation rate, we obviously want a non-constant bubble. So we've made two kind of mistakes there, on top of getting this imaginary part, and on top of putting the real part there as rather ad hoc. So this is my summary of the status of nucleation theory, taking us to halfway, so I'm roughly on time. Basically, at high temperatures, it's unclear what potential to use in the bounce or the bubble equations. Nothing's derived from first principles, unlike at T is 0, where we have a pretty solid understanding of how to proceed. And the obvious guesses are clearly wrong. So the tree level potential doesn't work, the effective potential doesn't work. Now there's the real part, and this has been recognized by many authors. On top of that, I pointed out that Affleck and Linder gave different prefactors. They gave different terms out front of the exponent. They're not the only people to have proposed prefactors at high temperature. I also write here the prefactors by Langer and Arnold and McLaren. And yeah, we have at least 4 different prefactors. So this lambda minus is the negative mode. Eta here is a decay constant, and psi is a different decay constant. So this is my understanding of the status of thermonucleation theory. Is classical, that was for QFT, is classical nucleation theory doing any better? I'm going to give a kind of a little bit of an overview of that, starting from the idea of classicalisation. Kind of intuitively, we know that at high temperatures, all the quantum effects get washed out, but you can also see this at a mathematical level. The place to start is the Bose distribution, in which bosons are distributed, and looking at the infrared modes, so those modes which have energies much smaller than temperatures. So if you start from this Bose distribution on the bottom there in your mind, you think about E being much smaller than T. So it's E to the small number. Then you Taylor expand that. You get 1 plus small number minus 1 on the denominator. The ones cancel, and then you get that the Bose distribution goes like T over E, where E is much smaller than T. So then you get these kind of basically large occupation numbers. And large occupation numbers tells you that you're going to start to get something classical. And in fact, many authors have looked at this, and the dynamics of quantum field theories of the infrared degrees of freedom of quantum field theories is quasi-classical. And so if what I've defined here as the nucleation scale, some kind of energy scale which defines nucleation, some energy scale of the bubbles, if that's much lower than the temperature, then and these are bosonic modes, then we have a chance that classicalization might happen, that these modes might become classical. And then there should be a quasi-classical description where the thermal and the quantum fluctuations give stochasticity. And that allows us, this classical description reproduces exactly the results of the quantum theory for classically, and basically it allows you to calculate quantities which are kind of have a good classical limit, like this one here, 5,5 plus 5,5, where you switch the order. So this thing has no anti-commutative part, has a good kind of classical limit. And these kind of things, quantities can be calculated in effective classical theories, kind of order by order, reproducing the quantum field theory results. There are definitely subtleties here, and it depends very much so on the particular degrees of freedom you have in your theory. But going on to the classical theory, this is the classical nucleation theory section. Classicality means that we have probabilities. We don't just have amplitudes anymore and complex numbers. We have a probability distribution, which I'm going to call rho, and we can define that on phase space. Here you can think of phase spaces in terms of phi I and pi I, some conjugate coordinates, and you can lump them together into eta I, which is just your phase space. And if we didn't have any stochasticity, if this was just pure classical smooth dynamics, we would have basically Hamilton's equations. You have written the Hamiltonian as some effective free energy. You can think of it as an effective Hamiltonian. It's this capital F, subscript F, FF. Anyway, so these first two terms would give you the dynamics of just a purely classical theory with no stochasticity. But then because you have fluctuations, both from quantum fluctuations and thermal fluctuations, you have additional terms. And this is what I've written here is basically the generic Fokker-Planck equation. Though being a Fokker-Planck equation, well, in some sense, there are some assumptions on the dynamics that have gone in here, but it's fairly general, but not completely general. Anyway, the crucial thing is we have a probability distribution, and because probability is conserved classically, that means you can write the Fokker-Planck equation as a continuity equation. So this term here, the time derivative of the probability distribution, can be equated to the divergence of a flux, or minus the divergence of the flux. So we have a continuity equation for probability. I haven't explained these fluctuation terms. It's a little bit complicated. These gamma are decay constants. The dependence here is such that you will end up reaching the Boltzmann distribution typically if you run for a long time. Just a quick example of a system that could be described in that way. If you had a Langevin equation for some scalar field which has a Klein-Gordon operator and then some potential dynamics, then it has dissipation and it has fluctuations, where these fluctuations are just random kicks, Gaussian random kicks, then this theory is describable by this Fokker-Planck equation. So assuming we have those dynamics, we now have a probability distribution, we have a probability flux. We can ask questions in phase space about what our probability flux and probability distribution does. And so this this picture here is copying a picture from Lange's paper, and it follows on from work by Kramers originally in 1940, and then followed up also by Zeldovich on classical point particle mechanics, like escape of a particle with thermal fluctuations. And you imagine that you start in some metastable region, and then you look at asking, after how long do I escape the metastable region? And you can do this in this probability distribution way, and then you look at the kind of lines of probability flux going from the metastable region to the stable region. But in order to do so, you need to kind of define these two regions. This is an infinite dimensional space that I've drawn on this 2D plane. This is, or in principle, infinite dimensional, as many dimensions as you want. This is the phase space describing the theory. So you can, in order to split up the phase space, you can define a transition surface using this effective free energy. So sorry, I'll just go back, this effective Hamiltonian / effective free energy, which determines the dynamics, also determines the probability distribution, or the Boltzmann distribution that you reach. So looking at the Boltzmann distribution, or looking at the effective free energy, there's going to be a kind of minimum at the metastable region, and then another minimum at the stable region in terms of that effective free energy. And you can draw a line between the two, being defined as the separatrix between the two, so that gradient flows go either to this way or to that way. And this you can define as the transition surface. So that this will be the maximum, essentially, between the two phases. So if you're going from here to there, you have to cross a hill. The transition surface is the hill. And then the idea was one can define the nucleation rate in terms of the probability, dotting the probability flux with the transition surface. So you ask how much probability flux is going through this transition surface. In the case where you start in the metastable state, in the metastable region, and you're kind of thermally populated in the metastable region itself, and you're not populated at all in the stable region. So on the right, there's nothing, and on the left, if you go far away from the transition surface, you're in the equilibrium. So with those boundary conditions, you can set up this problem. And in the semi-classical case, what matters is this region in the middle, which is, if you imagine I'm going from here to there and there's a hill in between, it's the lowest point on the hill. And that's the saddle point, which will define in the end the critical bubble. And this problem was set up in the region of the saddle point, expanding to quadratic order, this effective free energy. Here I've shown, kind of zoomed in on that. This picture here is a zoom in. You can see the transition surface in black. The minimum on the hill between the metastable region and the stable region on the far side is the critical bubble. Yeah, and we've kind of zoomed in, and we now can, everything's quadratic. And solving this problem in this quadratic free energy, so the equations basically become linear. You can show, or it was shown, that the current factorizes. So this is a non-equilibrium problem, and the non-equilibrium physics factorizes into a product of two terms. There's a non-equilibrium term, which depends on only a single scalar variable, u, and u is perpendicular to the transition surface. So it varies perpendicular to this transition surface. And so it's that non-equilibrium term multiplied by an equilibrium term. So within the transition surface, everything is in equilibrium with everything else in the transition surface. And also along these white dotted lines, everything is in equilibrium along the white dotted lines within the white dotted lines. And only perpendicular do you have anything non-equilibrium. As a consequence, the rate factorizes, the nucleation rate factorizes into a product of a kind of non-equilibrium and an equilibrium term. And I'm going to call this equilibrium term sigma, capital sigma, or the statistical part of the nucleation rate, or the equilibrium part of the nucleation rate. And it has a very simple interpretation. So there's a normalization, but then we have an integral over all the states, Boltzmann weighted by this effective free energy, and with a delta function which says that the negative mode is fixed at 0, or rather that we're on the transition surface. This delta function tells us that we're on the transition surface. So this is just the Boltzmann weighted transition surface area. This factorization was shown to hold at one loop order, basically within a kind of statistical kind of loop expansion. Yeah, so that's the kind of key result of classical nucleation theory. And I'll move on to the main stuff. Sorry. The effective field theory approach to nucleation. Sorry. Thermal bubble nucleation, rather. So the idea is, can we use EFT to resolve the inconsistencies I mentioned before? And can we make contact with classical nucleation theory? Can we identify this effective free energy, and can we calculate this capital sigma, which is kind of the easier, the equilibrium quantity to calculate? And this is the kind of paper that I'm talking about. Just to give us a background for the perspective, we're thinking about a top-down EFT because we know the QFT, and we're just calculating the low energy theory from it. And it's an easy case. It's not like QCD, where the kind of degrees of freedom at low energies are like super different from the degrees of freedom at high energies. So you write down all the symmetries, and then you write down all the possible terms. In some senses, we're in an easier case where we could do that, but it would be essentially equivalent to just integrating out the UV modes. So imagine we have some degrees of freedom, phi and chi. We split them based on their energy. Here on this line here, this is energy, higher energies up and lower energies down. Capital lambda is our cutoff, our split. Everything above capital lambda is high energy, and everything below capital lambda is low energy, or infrared and UV. I'm assuming we're in a case where phi has a low mass, so it has IR modes, and chi has a high mass. So all of its energies are above capital lambda, so it has no IR modes. But of course, phi also can have UV modes, because it can have high momentum. So starting from the partition function or path integral, you can integrate out the UV modes. You just kind of split up the measure, do the integration of the UV modes, and that defines your effective theory for your IR modes. And you have to carefully power count to make sure that dependence on capital lambda cancels. And you also need a hierarchy of scales for that to happen. So in terms of this, can we solve inconsistencies? There's a positive outlook, I would argue, for EFT. Thinking back to this real part of the effective potential, or kind of effective potential double counting problems. Imagine we wanted to calculate the nucleation rate, and we thought, okay, we can start with some effective theory. By the definition I just gave of this effective action, we can just shove in that it's equal to the logarithm of these integrals over the UV modes. And you can see as a consequence that there's no double counting. The IR modes are counted once out front, and the UV modes are counted once up in the exponent. Nothing's double counted. Also, kind of nothing's ad hoc, because this e to the logarithm just cancels, and I just get back my original partition function. So yeah, I didn't have to kind of go into the partition function and add something by hand. This all happens rather naturally. So there are no ad hoc steps, and each mode is counted once. So this was kind of discussed in this context by Eric Weinberg, but I'm sure that other people have discussed it. But yeah, for EFT to work, you need a hierarchy of scales. And I'm going to argue here that it's actually not such a crazy idea that there would be a hierarchy of scales. So for there to be a phase transition, a thermal phase transition, you need the thermal fluctuations or quantum fluctuations to modify the Lagrangian at leading order. So this is not completely true in all possible cases, but it's mostly true. The idea is that these fluctuations should change the phase structure of your Lagrangian, of your potential. And for them to change the phase structure, there kind of has to be some kind of order one or leading order correction. So you think of your effective Lagrangian as being your tree Lagrangian plus fluctuations. Fluctuations, because the ratio of those two is generally of this form, because these are loop fluctuations necessarily. There's some coupling constants out front. If you have a bunch of different degrees of freedom, there's some n for the number of degrees of freedom. And then there's a ratio of scales to some power. And that power is positive because the Lagrangian has positive mass dimension. So if we're going to have a modification at leading order, this thing should be 1, but it's suppressed by couplings. G is small. And if G squared n is small, if we're imagining this is the kind of nice perturbative theory, then the only way there's basically only two ways we can get to this being order 1, and that's either if our coupling is order 1, in which case it's not really perturbative. Potentially there's some large n limit that's going to work, but yeah. Or if there's a hierarchy of scales, and if the fluctuating modes which give us these large corrections are much larger than the tree level ones. This is also kind of obvious from a hierarchy problem kind of perspective. The high energy modes give you the big corrections. The low energy modes give you the small corrections. That's why there's a hierarchy problem. But in this case, it's not a problem at all. This is going to help us. But when zooming into the thermal case, we're looking at this equilibrium capital sigma. Equilibrium thermal physics can be formulated in this imaginary time formalism, where there's a time direction, which is not really time, but it's a circle, and it has size 1 over t. You can then Fourier expand your fields in this imaginary time direction, so you get purely spatial fields. With then Fourier e to the I and n pi t, where for bosons n is even and for fermions n is odd because of different boundary conditions. So then you get this infinite set of modes, and your theory then becomes basically a classical theory or a three-dimensional theory involving an infinite number of fields. And the masses of these different fields, or Matsubara modes as they're called, are like the true level masses plus a correction, which is n pi t. And this correction means that all the masses are kind of order pi t, except for the one which has n as 0. And so there's n equals 0 modes are special. They only happen for bosons, and those are the ones that can get infrared enhanced, can classicalize. So for those modes, if we look at their if we look at the potential of those modes, or the potential the corrections from from the other modes to the zero Matsubara modes. So yeah, you can see that essentially in effective potential, the leading corrections to the effective potential from thermal physics are to the mass, to the effective mass of this zero Matsubara mode. So you have the tree level term, and then you have this leading term, which is basically always roughly of the same form. You have the coupling constant, and then you have temperature squared. There's kind of nothing else it could be, just based on dimensions. And at high temperatures, this dominates. So if you look at this blue line, this is the high temperature case, where the effective correction to the mass means that the potential is just positive everywhere, or it's just convex everywhere. Whereas at low temperatures, we could in principle have a negative mass, and we can have two phases. And then at intermediate temperatures, there will be a critical temperature at which these two balance. So the fact of hierarchies of scales, there are kind of two reasons here why there are hierarchies of scales. At high temperatures, this term always wins. And because this term always wins, that means your effective mass is always GT. And GT is much smaller than pi t. So at high temperatures, there's always a hierarchy of scales. The zero Matsubara mode is always highly occupied. In addition to that, near the critical temperature, if you look at these plots, there's some kind of magic cancellation that happens at the critical temperature, and that happens within the mass, the effective mass. So at the critical temperature, this m squared and this g squared t squared term, they have some relatively good cancellations, which means that the effective mass can become smaller even than GT. So then there's kind of potentially an additional hierarchy. So high temperature effective field theory is not a new thing. Here I give an example of QCD. Its application to QCD has been applied also to the standard model. And here are some kind of early works on this from the 90s. So on the left-hand side, I've included all modes, and the Lagrangian on the left is that of QCD. So I haven't included mass terms, but so there's the gluon fields, and then there's the quark fields. And at some temperature, some high temperature, we have all these non-zero Matsubara modes plus the zero Matsubara modes. And so there's the thermal scale pi t, and then there's the potentially lighter scales. You can integrate out the scale pi t. That's called dimensional reduction, because that means you go from your kind of 3+ circle degrees of dimensions to just 3 dimensions. The circle disappears at that point, because you only have the zero Matsubara mode, which doesn't have which doesn't depend on that circular direction. So integrating that out, you remove the quarks, because all the fermions have only non-zero amounts of baryon modes. So you can see in the middle here, I have the effective theory at the scale GT, where the pi t scale has been integrated out, and this contains the gluons, both the spatial components and the temporal components, and the temporal components get a kind of a mass correction, a Debye mass correction is MD, which is of scale GD. The spatial components don't, so they're naturally lighter. So you can actually go further and integrate out these A0 fields, which have this kind of intermediate mass of GT, and you're left with on the right, just a theory valid on the longest scales, G squared T, which only has these kind of spatial gluon degrees of freedom left. And in practice, how that's done is by matching. I guess I'm preaching to the converted, but anyway. So you match correlation functions in the infrared. You demand that the correlation functions agree in the infrared, and by doing that, you can fix the coefficients of the EFT. And as an example here, we have this sunset diagram where the external lines, the full lines are infrared lines of the light particle, and the dotted lines are the UV lines, and that splits up into a sum of two terms. Basically, this heavy particle, the dotted line particle, shrinks, the loop shrinks to a point, and then the hard line may shrink to a point if inside the loop the light particle gets a high momentum, basically, or may not shrink to a point if inside the loop the particle doesn't get a high momentum. So you get these kind of two contributions from this sunset diagram. And the diagram, if you think about it as in terms of its momentum dependence, in the full theory, it's complicated. It's non-local in the sense that it depends on P in a complicated way. And because of a hierarchy of scales, you can expand it, and that's why it kind of simplifies into these dots, which are just kind of much simpler in terms of their momentum dependence. And splitting the calculation in this way, first constructing the EFT, and then doing calculations within the EFT. By doing that, the effects of the heavy particles on the light particles are resummed. For Bob nucleation, we need to identify the nucleation scale EFT. I defined this nucleation scale capital lambda before, and I just want to point out here that nucleation scale should be it should be able to describe the bubbles. It's not zero, and it's not too high. It has to be a scale at which the bubbles vary. That's the scale we want to describe. And given the bubbles are a saddle point of the nucleation action, the various terms in the nucleation action must balance at the saddle point. Essentially, there's some kind of virial theorem or a Derrick's theorem or something which tells you that these terms must balance. And balancing these two most obvious terms, you get that the derivative basically is like the mass. They should be of the same order, and hence the scale on which the bubble varies is like the mass. This is not surprising, but essentially the nucleation scale EFT is the scale of the mass of the nucleating degree of freedom. Is the EFT which describes the scales of the mass of the nucleating degree of freedom. And to construct it, we integrate out all modes greater than the nucleating scale of the nucleation scale, or rather with coarse grain over distances smaller than this inverse nucleation scale. Now going back to classical nucleation theory, so I'm getting to the end now. The starting point of classical nucleation theory is this effective free energy, describing the length scales of the nucleating bubbles. And due to factorisation, we can calculate the main part of the nucleation rate in equilibrium. Now, high temperature dimensional reduction, as I just described, integrates out all these non-zero Matsubaru modes and hence all the quantum fluctuations, leaving just these zero Matsubaru modes, which are a classical effective theory for those zero Matsubaru modes in equilibrium. Hence, we have, by integrating out all of both the thermal scale and any intermediate scales, or coarse graining, we can identify this classical effective description with this nucleation action. And by so doing, we then get essentially an unambiguous definition of the nucleation rate for QFT at high temperatures, using classical nucleation theory. So we start in our QFT, we derive a classical effective theory, and then we know what to do in the classical theory to get the nucleation rate. It's kind of well defined in terms of probabilities of escaping and so on. Yeah. And this resolves many of our previous inconsistencies. So the nucleation action is perfectly real. We don't have any problems with imaginary parts. The derivative expansion is perfectly justified because we have some hierarchies of scales. And each of the modes is only counted once. So I mentioned this before, but in terms of the nucleation, the equilibrium part of the nucleation rate, all the high energy modes go into the exponent, and all the low energy modes go into the prefactor. Everything gets counted once. And using EFT in standard EFT methods, you can ensure that the result is independent of this cutoff scale, order by order, as long as the cutoff scale is kind of between the appropriate ranges, then you can get order by order independence. Okay, I have an example here, but maybe I don't have time to go into the example. The example is the cubic anisotropy model. This interestingly has 3 scales. There's an intermediate scale, a low energy scale. There's a hierarchy of masses whenever there's a first order phase transition. The two are intimately coupled. Basically, for the arguments I gave before, you need a hierarchy of scales, otherwise you don't get a first order phase transition. And by doing the matching, doing the integrating out, we can get a final result for the statistical part of the nucleation rate. You can do the power counting, and you can find that you can get small corrections. Interestingly, you find that not only is there some kind of, but basically there's a subleading but still exponentially large contribution, this C over square root of G term, which comes from 2 loop corrections, and you kind of wouldn't have spotted maybe had you not carefully power counted in an EFT way. So just doing a kind of naive 1 loop calculation, you maybe wouldn't have spotted this. And anyway, this in this EFT approach, both these A, B, and C, they're all perfectly calculable and well defined and so on. And independent of the matching scale, all seems good. Anyway, that's my conclusions. So the first 2 are from the intro. Basically, phase transitions can give us observable effects like gravitational waves. The bubble nucleation rate is potentially a limiting source of uncertainty for predictions of these gravitational waves. There are many problems in this bubble nucleation rate, and I think using this EFT approach gives us an unambiguous definition of the nucleation rate for QFT at high temperatures by building a bridge to the classical nucleation theory. And it resolves a bunch of inconsistencies which have stood for a long time, and it also facilitates higher order calculations. As I pointed out at the end there, you can get these 2 loop parts and so on. That's it. Thanks for listening.